Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be evaluating an infinite complex radical. Can you imagine? Infinite complex radical. You got it all. So we've done some problems like this before with real numbers like square root of 2 times the square root of 2 times the square root of so on and so forth. And then we kind of thought about some sequences, the terms of a sequence, and then how they grow, and if there's a limit, so on and so forth, right? There's a lot of stuff involved. But this time we have I, and I'll be presenting two methods. Now, first of all, does a sequence like this converge? And by the way, how do you define the sequence? You could probably define it as follows, like suppose a sub 1 is equal to square root of I, and then a sub 2 is just going to be square root of I times the square root of I, which is kind of like I times a sub 1, that would be a sub 2. And in general, you kind of define a sub n as the square root of I times a sub n minus 1, where a sub 1 is equal to square root of I. And of course, n is supposed to be greater than 1, so we don't end up with a sub 0, right? Obviously. Okay, so we can kind of define our sequence that way, and then do you think this is going to converge, right? Well, how do you determine if this is going to converge with complex numbers? That's a different story, but I'm just going to present two methods, and I'm not going to go into the limits or the convergence and all that complicated stuff. Okay, let's start with the first one. First method, we have the square root of I times the square root of I times the square root of I. Actually, I can kind of talk about three methods here. I just remembered there's another way to approach it using a really nice approach. Anyways, we'll talk about it later. So we have this interesting infinite product, infinite radical expression, and I want to evaluate it. Suppose this is convergent and this is equivalent to x. So what does that imply? I can approach it in two different ways. This expression contains itself infinitely many times. So one way to approach it. The second way to approach it is squaring both sides. That's a little safer. Let's square both sides, and the outer square root is going to disappear. We're going to end up with I times the square root of I times the square root of I times the square root of I times. You get the idea? We are getting the same thing. Of course, that's the whole idea. This is the same thing as x. And this is really nice because it kind of makes it more clear that, oh, okay, this expression really contains itself, right? And then from here we get the following. Ix equals x squared. Now, if I didn't follow this approach and just went straight to this, let me show you an alternative approach. If I just directly went for the inside, set it equal to x, and then realize, this is the same thing as x, so we have square root of ix equals x. This would be an interesting question, something to talk about. We have the square root of I, but I has two square roots. So whatever we find for x, are they both going to satisfy? And did I say both? Because I am assuming there's going to be two solutions. Well, we got to check it out. But anyways, that's something that I wanted to introduce real quick. And let's get back to our equation. We have ix equals x squared. So let's go ahead and write it this way. This kind of looks a little more intuitive. And then put everything on the same side. And then take out x. Don't ever cancel out things because you're going to lose solutions. Okay? So we got this nicely factored form. And from here, we can say that, hey, x is either 0 or x is I. So here's the problem. X equals 0 does not satisfy the original expression. Like satisfy? I mean, the original expression cannot equal to 0. In other words, why? Because you're multiplying I, square roots of I, whatever, and this is not 0. Probably not, right? I mean, there's no 0 in the product. So how can... That's something interesting about 0, that if you don't have any zeros, the product cannot be 0. That's a very powerful rule for 0. Annihilation. Anyways, so 0 is not acceptable. But here's the thing. If you consider this equation, ix, square root of ix equals x, then 0 works. Why? because if x is 0, the square root of 0 is 0. This is actually true even in the complex world, right? Isn't it? As far as I know. But it doesn't just express our original expression. It's not 0. We know that. So the answer is I then. Wow. This whole thing was equal to I? Looks like it. Let's go ahead and talk about the second method, and then I'll talk about an alternative approach. Okay? The third one. So the second method uses something different. And consider that, remember we talked about sequences, right? Now whenever you have a product, you can actually turn this into a sum of powers. Okay, so we're going to go ahead and use the idea of rational exponents. For example, when you have the square root of x, it can be written as square root of x to the power 1/2. If you have the cube root of x, you can write it as x to the power 1/3. The problem being, if x is negative, and when you talk about a square root, there's going to be 2 square roots. I is complex, there should be 2 square roots. So that's a little problematic. Which square root are you talking about? Which fourth root are you talking about? And the problem gets worse and worse because I has 2 square roots, but it has 4 fourth roots. You see the idea? Okay, cool. Anyways, let's just assume everything works nicely. I know that's an oversimplification, but let's go ahead and consider the first I. That is under 1 radical, so we can write it as I to the power 1/2. Now this I is the square root, if you just totally ignore this. It's kind of like the square root of the square root of I, and that can be written as I to the power 1/4. And this guy here is going to be I to the power 1/8, so on and so forth. Guess what gives you, this gives you? This gives you an infinite geometric series. So we can write it as I to the power 1/2 plus 1/4 plus 1/8 and so on and so forth. But we know this sum, 1/2 plus 1/4 plus 1/8, if this is an infinite series, and we know it converges because the R value is 1/2, which is less than 1 and greater than -1. It's going to be a sub 1, first term, divided by 1 minus R, which is 1. So this whole thing is equal to 1. I to the power 1, as far as we know, is equal to I. So this expression is equal to I again. One more time. Yay! I wins. I win? No, I wins. Okay, I don't win. So here's a third approach. The third approach kind of uses a shortcut, so I know some people may not like it. Like, how on earth do you know these things, right? Well, it kind of comes from the other methods. But whenever you have something like this, and I think I talked about these formulas before, this is equal to x. If you have the sum, that's a different story. Then you kind of have to factor x into 2 numbers, a and a plus 1, and it's going to be a plus 1. If it's a minus, it's a, so on and so forth. But yes, we have a shortcut, and by the shortcut, this is equal to I. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.